Welcome back to lesson 5-6. This is part 1 of 2 on inequalities in one triangle. And we are going to talk about the special relationships that occur in sides and angles of triangles. And we're going to limit it in this lesson to just one triangle and look at what different kinds of properties exist between the angles and the sides. And the first property we're going to talk about is called the comparison property of inequality. And basically what that says, if you have any length A and it's equal to the sum of two other lengths and neither of these are 0, then A has to be bigger than B and A has to be bigger than C as well. But we're just saying if C is a number bigger than 0, A has got to be bigger than B because you're adding something to B to get A. So it's pretty logical, pretty straightforward, even though that might be confusing in the algebraic terms. It's just saying A has to be bigger than B if you're adding something to B to get A. So from that same property, we can get this corollary to our triangle exterior angle theorem. Now remember, an exterior angle is an angle outside of a triangle that is formed by extending one of the sides. So in this example, angle 1 is an exterior angle. And then a little review, angles 2 and 3 inside the triangle are called our remote interior angles. So 1 is an exterior angle, 2 and 3 are remote interior angles. And the relationship, just to review, that exists between these three angles is that angle 1 is equal to the sum of angles 2 and 3. So in this corollary, angle 1 is an exterior angle, then we know that angle 1 is greater than angle 2, and we also know that angle 1 is greater than angle 3. Now don't misinterpret this corollary to say that angle 1 is greater than the sum of 2 and 3, because that's not true. It just says that angle 1 is bigger than angle 2, and angle 1 is bigger than angle 3. Either one individually, but not the sum. So be careful of that. So here's an instance where we can apply this corollary to solve a problem. It says, why is the measure of angle 2 greater than the measure of angle 3? Why is this angle down here bigger than this angle up here? Well, when we just look at that, it doesn't seem obvious to us. So we have to actually go through and analyze what we're given in this picture. And when you look at this picture, we have a triangle ABD right here, triangle ABD. And angle 1 right here is an exterior angle to triangle ABD. So that's our first piece of information, is angle 1 is an exterior angle to triangle ABD. So we know that angle 1 is bigger than angle 3 and angle 1 is bigger than angle 4 because it's an exterior angle. 3 and 4 are remote interior angles. And then we also have this triangle BCD right here. And in BCD they tell us that side BC and side DC are congruent. Okay, so since those are congruent, we also know that angle 1 and angle 2 are congruent. That's the converse of the isosceles triangle theorem. We've learned that from another chapter. Since these sides are congruent, that means the base angles are congruent. Well, now we have angle 1 and angle 2 are congruent, and we said some things about angle 1 up here. So we could substitute angle 2 up here for angle 1 since they are congruent. So when we substitute angle 1 in this first statement, we would get angle 2 is greater than angle 3, and angle 2 is greater than angle 4. And that was what we were trying to prove, was that angle 2 is greater than 3. So just by substitution, we proved that angle 2 is greater than angle 3. Here's one for you to try, very similar. Why is the measure of angle 5 greater than the measure of angle C? In the same drawing, why is this angle right here bigger than angle C over here? Go ahead and pause the video, see if you can think on that and come up with some logical reasoning, and I'll give you the answer when you come back. Alrighty, I hope you gave that a try. Why would angle 5 be bigger than angle C in that figure? Well, angle 5 right here, it is an exterior angle to triangle ACD, this big triangle. Okay, angle 5 is an exterior angle. So you could start out by saying that angle 5 is an exterior angle. If it's an exterior angle, then angle 3 and angle C are its remote interior angles, right? Angle A, which is angle number 3, and angle C are remote interior angles. of that same triangle. So we know that angle 5 is bigger than either of its remote interior angles, so we can say, therefore, angle 5 is greater than angle C, and which is what we were trying to prove. So here are a couple of theorems for you that we will be working with in this section. The first theorem, 510, basically says if you have two sides of a triangle that are not equal, and one of them is bigger than the other one, the longer side is opposite the bigger angle. Okay, so in this example, we have segment XZ is the longest side, and it's bigger than XY. So this side that's the longest, its angle that it's opposite to, angle Y, has to be bigger than angle Z, just because the sides are longer. Likewise, in theorem 511 here, when we're dealing with the angles, if we have an angle, one angle bigger than another angle, then that angle has to be opposite the longer side. So if angle A is bigger than angle B, then that means BC has to be bigger than AC. Remember, it's the opposite side and the opposite angle. So here's an example how we could use this. Let's suppose we have a town park and it's triangular in shape, and the architect wants to put a bench at the corner that has the largest angle. Which two streets form the corner with the largest angle? Well, we're given the lengths of each of these roads, each of the sides of the triangle, and the longest one is Hollingsworth Road. Okay, so since this is the longest side of the triangle, it has to be opposite the biggest angle. So the angle would be the intersection of MLK Boulevard and Valley Road. So since Hollingsworth Road is the largest street, or the longest street, then MLK Boulevard and Valley Road form the largest angle. So here's one for you to try. Suppose the architect wants to put a drinking fountain at the corner that has the second largest angle. Which two streets form the corner with the second largest angle? Well, we know this one is the largest. What's the second largest road, the second longest? And that would be the Valley Road. So the angle that's opposite that side would be this angle right here, and it's the intersection of MLK Boulevard and Hollingsworth Road. So the solution to that one would be MLK Boulevard and Hollingsworth Road. Here's an example with theorem 511. Which choice shows the sides of triangle TUV in order from shortest to longest? Okay. Well, in order to get the lengths of the sides, or know anything about the lengths of the sides, we need all three angle measures. So we need to figure out what angle T is equal to. And angle T is equal to the sum of these two angles subtracted from 180. So once we solve for angle T, we find that T is equal to 60 degrees. So now we can put the angles in order from smallest to largest. And we get angle U is smallest, angle T is the second, and angle V is the third. It's the biggest one. So now we just need to order the opposite sides. Angle U right here is opposite side TV. Angle T up here is opposite UV. And angle V, the 62-degree angle, is opposite TU. So we just need to substitute the opposite sides. So therefore we can see that choice A is the correct answer. Here's a problem. It says in the figure at the right, angle S is 24 degrees, angle O is 130. Which side of the triangle is the shortest side? And explain your reasoning. Well, we need to find the smallest angle first of all. So we know angle S and we know angle O. We need angle X. The measure of angle X is equal to 180 minus the sum of the other two. And when we figure that out, we get 26 degrees. So when we look at the angle measures, we have a 24, 130, and 26. Angle S is the smallest angle. So then the opposite side, which is OX, has to be the shortest side. Here's your lesson check. Which is the longest side and which angle is the smallest? Bring your answer to these to class and we will talk about them then. See you next time.